So today's class is Nuclear Physics Lecture 2. So once again, today we will be starting with the first unit of the special paper on nuclear physics, that is nuclear and particle physics, in which the first unit is general properties of nuclei. So yesterday we have started the discussion on first unit, general properties of nuclei, and in this we have started discussion on the constituents of nucleus, what a nucleus actually consists of, and the properties of components of the nucleus. And we have also tried to understand the quantitative facts about properties of nucleus, that is size and mass. So two things we have tried to understand yesterday. We tried to know about size of nucleus and mass of nucleus, and in turn we have understood mass defect. Today we will continue to discuss the other properties, that is density of nucleus, charge of nucleus, and the most important part of this topic, that is binding energy, which is a result of mass defect. So we have understood mass defect, and in today's class we will be trying to understand binding energy, and the most important is average binding energy per nucleon against a mass number curve and its main features. We will try to interpret this, and then the other properties may be parity, magnetic moment, angular moment, and electric moment of the nucleus. So yesterday we started with the Rutherford's alpha scattering experiment and results of alpha scattering experiment, that there were three important results: the atom with a whole mass concentrated at the center. When on such a structure, a beam of alpha particles is incident, many of the alpha particles went straight, which means that there is a lot of empty space. Some of the alpha particles scattered by 90 degrees, and 1 in 20,000 scattered 1 in 20,000 scattered by large angle, that is 180 degrees, because the incident particle is alpha particle is positively charged, and it is incident at a point where whole of the mass is concentrated at a point and it is positively charged. Therefore there is a Coulomb repulsion, hence the incident alpha particle has scattered by 180 degrees. Therefore Rutherford concluded that at the center of atom there is something as if whole mass is concentrated at a single point, it is positively charged, and he named it as nucleus. That is how the birth of nuclear physics by Rutherford in the year 1911. So we have seen that nucleus is spherical in size, radius is given by r equal to r naught a raised to 1 by 3. Because nucleus is very small, its radius is measured in Fermi. 1 Fermi is 10 raised to minus 15 meters. And also nuclear mass is because of what is there inside a nucleus. Inside a nucleus only protons are and neutrons are there, z number of protons and n number of neutrons, and their mass is zmp plus nmn. And the actual mass, that is real mass, is mass as a whole is less than the sum of separately weighed assumed mass. So therefore mass defect is equal to assumed mass, that is zmp plus nm minus real mass. So it is all together is less when they are weighed separately. This is known as mass defect. So which we are going to continue today's class. So we'll start with the density of a nucleus. We all know that it is normal density is mass by volume. Oh, there should be some correction here. It is See, nuclear density is nuclear mass by nuclear volume. Nuclear mass by nuclear volume. Mass by volume is density. So, on same, see, nuclear mass, this term should be nuclear mass, correct this as nuclear mass. So, nuclear mass is A is total number of nucleons. A, capital A is mass number, which gives number of protons plus number of neutrons into Mn. Amn into Mn. Mn is average mass of nucleus, mass of proton plus of mass of neutron divided by 2, because proton and neutron are approximately equal mass. Therefore, we take average mass. A is total number of protons and neutrons. So, A into Mn, the numerator A into Mn will give you mass of the nucleus, nuclear mass, divided by volume. So, nucleus is spherical in shape, therefore, volume is 4 by 3 pi r cube, where r is radius of the nucleus. Mn is mass of the nucleus, it is 1.67 into 10 raised to minus 27 kg, and A is mass number, which is protons plus neutrons, and Mn is mass of proton plus neutron divided by 2. So, nuclear volume. So, if you calculate nuclear volume, it is a spherical shape, 4 by 3 pi r cube, 4 by 3 pi. This r is r naught into a raised to 1 by 3 by the radius expression. Capital R is equal to small r naught into a raised to 1 by 3 whole cube, and r naught is a constant. Its value is 1.3 into 10 raised to minus 15 meters. A is mass number, protons plus neutrons. So, nuclear volume is 4 by 3 pi r cube, 4 by 3 pi. For capital R, we have substituted r naught into a raised to 1 by 3 whole cube. So, it is 4 by 3 into pi r naught A. Then nuclear density is mass is A into Mn divided by volume. Mass by volume, mass is A into Mn. A is total number of protons plus neutrons. Mn is mass of average mass of nucleon. So, therefore, A in the denominator, A in the numerator gets cancelled. So, it is Mn divided by 4 by 3 pi r naught cube. So, you look at this expression very carefully. See, nuclear density is equal to Mn, which is mass of average mass of nucleon, that is 1.67 into 10 raised to minus 27 divided by 4 pi 3 pi r naught cube, where r naught is a constant, which is equal to 1.3 into 10 raised to minus 15 meters. So, if you look at this, it is very interesting to see that nuclear density is independent of A. A is total number of nucleons. So, it is so dense that it is independent of capital A, and that is mass number, total number of nucleon it's in it. So, the magnitude of nuclear density is Mn is 1.67 into 10 raised to minus 7 divided by 4.3 into pi r naught cube, and you end up with the simplified answer is 1.16 into 10 raised to 7 kg per meter cube. So, you look at the magnitude, it is plus 17. So, the density, nuclear density is very large. Nuclear density is very large. So, therefore, what Rutherford said is, inside an atom, whole mass of the atom is concentrated at a single point, which is positively charged. As if whole mass is concentrated into a single point, it means the density at that point is very large, and you can see how large it is, 1.8 into 10 to the power plus 17. So, this kind of high density, very high density is seen in the stars, that is white dwarf, where the inside the atom, because of this density, the outer orbits, electron cells also collapse, and the very dense matter is the nuclear density range, that is 1.816 into 10 raised to 7 kg. So for nuclear density, it is nuclear mass by nuclear volume. Nuclear mass by nuclear volume. So it is equal to mass is A, total number of protons plus neutrons, into Mn, that is average mass of a nucleon. A into Mn is mass of nucleus divided by volume, because it is spherical, 4 by 3 pi r cube. So nuclear volume is 4 by 3 pi r cube, where capital R is R naught into A raised to 1 by 3 because of yesterday's equation cube. So it comes out to be 4 by 3 pi R naught cube A. So nuclear density mass is Amn divided by volume 4 by 3 pi R naught cube A. So we end up with an expression Mn divided by 4 by 3 pi R naught cube, where the nuclear density is independent of mass number A, and the final result is of the order of 1.816 into 10 raised to plus 17 kg per meter cube. So very high density of the nucleus. Now the second property is nuclear charge. It's very simple. You know that what is there inside a nucleus. See, if you look at this, inside a nucleus there are protons which are positive and neutral neutrons. So there are protons and neutrons inside a nucleus, and the number of protons inside a nucleus is given by Z. Z gives only the number 1, 2, 3, 4 like that, and the unit positive charge is plus because it is positive charge. So total number charge on the nucleus is plus Ze. It is plus, Z is only number, plus Ze, and E is unit positive charge. So this unit positive charge is again plus 1.6 into 10 raised to minus 19 coulomb, which is opposite to that of electron. So unit charge is electron is minus, whereas proton is positive, but unit charge is plus 1.6 into 10 raised to minus 19 coulomb. So charge of nucleus is because of the number of protons inside a nucleus, and Z will give you how many protons are there inside a nucleus, and E is one unit charge. Therefore nuclear charge is equal to plus Ze. So nuclear charge is experimentally obtained by alpha scattering experiments. Now it is interesting part of the nuclear physics. So we have tried to understand, we tried to understand the mass of a nucleus, and we know that mass of nucleus when weighed together, that is protons and neutrons together, is less than when mass is separately weighed, that is proton mass of one proton, mass of second proton, mass of third proton, mass of fourth proton, and mass of one neutron, mass of second neutron, like that. So if you weigh them separately, then if you weigh them separately, so if you weigh them separately, the mass is different when you weigh as a whole. So therefore real mass and the assumed mass are different, and so we have seen that the difference between real mass and assumed mass is mass defect. And why mass is lost in keeping the nucleons of nucleus together is some energy is required to keep the protons, some energy is required to keep the protons, energy is required to keep the protons and neutrons together. So therefore keeping two protons, because both protons are positively charged, there may be a Coulomb repulsion, and keeping a protons and neutrons in a very small region of nucleus, some force is required, some energy is required to keep the nucleons of a nucleus together. So to get that energy, mass is lost, that we are calling as mass defect, and as per E is equal to mc square. So very small mass will give a enormous amount of energy, and that energy which is keeping the nucleons of a nucleus together is called binding energy. So, nuclear binding energy is the minimum energy that would be required to split the nucleus into its components. So, if you want to see, you have a nucleus in which there are many protons and neutrons, you want to separate them, then minimum energy required is the binding energy, then you can separate them into 4 protons and 3 neutrons. So, minimum binding energy is required to keep the nucleons of a nucleus together, or if you want to separate them, minimum energy required is the binding energy. So, binding energy is the minimum energy required to disrupt or minimum energy required to keep the nucleons of a nucleus together, that is nucleons of a nucleus together, that is neutrons and protons together, we call them as nucleons. So, nucleons, neutrons and protons together we call them as nucleons. So, if we want to just count number, then we say 4 nucleons, maybe 2 protons and 2 neutrons, like that. So, the mass of an atomic nucleus is less than sum of individual masses. This is what we have seen in case of mass defect, and missing mass is mass defect, and mass defect represents the energy released when the nucleus was formed. So, to keep the nucleus, energy is required. To break the nucleus into the protons and neutrons, minimum energy required is the binding energy. Then Z protons and n number of neutrons. Z will give how many protons, n will give how many neutrons. So, Z protons and n neutrons combine to form a nucleus where a mass delta m disappears, because energy is required to keep protons and neutrons together, and that delta energy is equal to delta E is equal to mass defect into C square. So, you look at this. So, nucleus as a whole, if you supply minimum energy required, then you can split into the nucleons. This energy is called binding energy. So, binding energy is the energy required to keep the nucleon intact, to keep the nucleon, protons and neutrons together, and if you want to separate them, then minimum energy required to split the nucleons into the protons and neutrons is the binding energy. So, now once again, so you can visualize, so keeping 2 helium-4, 2 helium-4 is a helium, that is alpha particle, that is Z is 2, A is 4. So, this 4 you can write this side also, 2 helium-4, 2 is number of protons. See, there are 2 protons and 2 neutrons. 2 protons is 2 brown colored, 2 neutrons is 2 white colored. So, 2 protons and 2 neutrons together, an alpha particle or helium nucleus, its mass is something. See, and when separately 2 protons, that is mass of this proton and this proton, and mass of this neutron and this neutron is weighed, so we get something different mass. When they are separately weighed, mass is more, 4.03188 atomic mass units, and as a whole mass is less. And so you can calculate the difference. As a whole is 4.00150, and when them 2 protons and 2 neutrons separately weighed 4.0318, the difference between real mass and assumed mass is 0.03038. This is mass defect. So, this is mass defect, and so this one you have to remember, mass defect is atomic mass units, and you can convert into energy units by multiplying with 931. One atomic mass unit, Akash mute mado, one atomic mass unit is equal to 931 MeV. 1 atomic mass unit is equal to 931 MeV. Therefore, 0.03038 into 931 will give you 28.28 MeV as binding energy. So, what is this 28.28 MeV? It is the binding energy of helium nucleus or alpha particle. That is energy required to split 2 helium-4 into 2 protons and 2 neutrons. It is the energy required to split the nucleus into 2 protons and 2 neutrons is the binding energy of 2 helium-4 nucleus or alpha particle. It is the minimum energy required is 28 MeV. Now, you can write more about binding energy. You can understand more that what is the use of this value. Binding energy gives us stability of a nucleus. We can understand from the magnitude of binding energy, because you know that you to keep the nucleons together, minimum energy required is to keep the nucleons of a nucleus together. Minimum energy required is binding energy, and to split the nucleon into its component, minimum energy required is the binding energy. Therefore, if the minimum energy required is very large, then nucleus is stable. To break the nucleus, if the energy is very small, then it is unstable. So, if the binding energy is large, nucleus is stable. Binding energy is least, it is unstable. So, you can write binding energy by an equation. So, this is the main bracket. Inside it is mass defect. Mass defect is, this is the assumed mass, first bracket. Z is number of protons into mass of proton plus N is number of neutrons into mass of neutron. So, this is the assumed mass in the first bracket, minus capital M is real mass as a whole nucleus. So, there is mass defect between this, and energy equivalent into C square is binding energy. If binding energy is greater than 0, it is stable. If it is least, it is unstable. So, you can calculate another example, binding energy of a deuteron. What is a deuteron? It is 1H2, 1H2. It is a 1 proton, 1H1, sorry, 1H1. So, hydrogen nucleus is only 1H, that is only proton is there inside hydrogen nucleus. If there is one neutron inside it, then 1 proton plus 1 neutron. 1 proton plus 1 neutron makes a deuterium. And if there are 1H2, as I have just mentioned, if there are 2 protons, 1H2, then it is a one proton and 2 neutrons, that is tritium, isotopes of hydrogen. So, hydrogen is 1 proton, that is 1H1, and deuterium or deuteron is 1 proton and 1 neutron, that is 1 proton and 1 neutron, it is 1H2. So, mass of proton is equal to 1.007276 atomic mass units, and mass of neutron is 1.008665 atomic mass units. So, this will be data will be given to you. So, knowing mass of proton and mass of neutron, if you add them separately, mass of 1 proton plus mass of 1 neutron is 2.015941 atomic mass units. So, this is the deuteron. Deuteron consists of 1 proton and 1 neutron inside the nucleus, 1 proton and 1 neutron. So, 1 proton is, that is 1H2, it is represented by 1H2. Mass number is 2, that is 1 proton plus 1 nucleon. So, whereas charge is only 1 because 1 proton is there. So, therefore, mass of proton plus mass of neutron is this, whereas directly as a whole mass of deuteron nucleus, together 1 proton and 1 neutron, they weigh 2.013553 atomic mass units. So, this is smaller than this is the real mass. Assumed mass minus real mass is mass defect. It is 0.002388 atomic mass units, and if you multiply, so you know that it is 2.23. So now you can just compare. The earlier example, binding energy was 28 for alpha particle or 2 helium 4, because there were 4 nucleons, 2 protons and 2 neutrons. So in this case of deuteron, there are only 2 nucleons, that is 1 proton and 1 nucleon. The binding energy is only 2.23 MeV. It is sufficient if you supply 2.23 MeV of energy to deuteron, so it will break into 1 proton and 1 neutron. That is how, from the magnitude of binding energy, so you can understand the stability of a nucleus. Now, this graph you have to practice how to plot. Observe carefully. It is very, very important graph. This graph is called average binding energy. See, average binding energy against mass number A. Mass number A is total number of protons and neutrons inside a nucleus. Average binding energy, average binding energy is binding energy divided by total number of nucleons inside it. So we have taken deuteron. Average binding energy is binding energy divided by 2, that is 1 proton plus 1 neutron. If it is alpha particle, it is average, that is binding energy divided by A, that is 4, because 2 protons and 2 neutrons are there. So average binding energy along y axis, average binding energy per nucleon along y axis, and mass number, that is 0, 1, 2, 3, 4, 50, 100, 150, 200 and 250. So you must be wondering what are these. See, so just to understand, from 0 to very small number 1, 2, 3, 4. So 1H1 is hydrogen. For very small mass number, 1 will be hydrogen, 2 will be helium, right? 1, this is mass number. So 1 will be hydrogen, 2 will be deuterium, 1H2. 1H2 is deuterium, and 2 helium 4. So 2 helium 4, 4 mass number will be helium, and like that. So you have 2 helium 4, 8 oxygen for 16, and 56 is iron. So when you cross this line, so 50 is here, 56 mass number 56 is here. This 56 is iron, Fe 26, iron 56, and when you move after this 100, 120 is tin, Sn, and if you cross the 200, so if you come this side, it is 238, mass number 238 is uranium. So these are called heavy elements because there are very large number of nucleons. Mass number is 238. So mass number is above 200. So they are 200 nucleons inside a nucleus. Therefore, its mass is heavy. It's a heavy nucleus. So uranium is 238. Okay, and these are light nuclei because there are only 2. Mass number is 2, 3, 4, 5, 8, 10, 16. Comparatively, these are smaller when compared to this, and in the middle range 50 to 150, 50 to 150 or 40 to 160. 40 to 160 is the middle range. This side they are small, light nuclei, and this side they are heavy nuclei. So we also know that, we will come to the point. This is written as fusion fission because we know that what is fusion. Light nuclei fuse to form, release energy. So lighter nuclei of hydrogen, helium, lithium, beryllium, they undergo fusion in this range and produce the energy, whereas heavy nucleon above 200 mass number, heavy nucleon above 200 mass number, when they are split, they release huge amount of energy. For example, energy 92U238, when it is hit by a fast moving neutron, it is split into barium and krypton, release of 200 MeV of energy. with 2 neutrons are released. This is fission process for heavy nuclei and fusion process for light nuclei. Like this, from the and these from 40 to 160 they are average, so they are very stable nuclei, so this can be understood from average binding energy mass number curve. So systematically we will try to understand the same curve, binding energy per nucleon along y axis. So it is in MeV, 2 MeV, 4 MeV, 6 MeV, 8 MeV, 10. So maximum is not 10, so maximum is only, this is 9, this is 9, 9 is also not there, so maximum is 8.8. So I will come to this point. So this is for iron. Iron is the maximum binding energy, so you know that very strong. So iron is 56, its binding energy is maximum 8.8. So for very light nuclei, so that is how you have to write. For light nuclei, binding energy increases. So this is binding energy for hydrogen, for helium, for lithium, so like this, and oxygen. So as you go, so the binding energy increases up to maximum 8.8. For mass numbers 40 to 160 is a flat, from here to here it is a constant binding energy, that is 8.8. Then it drops. So once again it drops from maximum to 7.6 for uranium. So 7.6 value. So this value is 7.6 for uranium. So that you can split the nucleon into lighter particles, which enables fission. So, and most important part is this region. So first it is very linear, binding energy increases as mass number increases for light 1, 2, 3, 4, 5, 6, and especially for mass numbers. So this is very important, you have to remember the mass numbers: 2 helium 4, 4 beryllium 8, 8 oxygen 16, 10 neon, 24 magnesium. Like this there are peaks, so which I will show you in the next slide. So these peaks, and then only in this region, and then it is a flat curve, and then this decreases. So once again you have to plot this and you have to write for very light nuclei, that is hydrogen and helium, lithium, beryllium, binding energy increases with mass number. As mass number increases 1, 2, 3, 4, 5, 6, 7, 8, binding energy also increases linearly, and it increases up to 8.8 MeV for iron, that is 56 mass number, and the binding energy curve is almost flat for mass number 40 to 160. It is a flat curve. So this, in this region the elements are stable because they have same binding energy, and for heavy nuclei more than 200 the binding energy decreases to 7.6 MeV, and you see peaks for particular numbers of mass numbers, which you can see here, that is the peaks for helium, beryllium, carbon, oxygen, and neon. Mass number up to 20, up to 20. So you can see. So this is up to 20 here, up to 20 or 24 also. 24 is magnesium, and afterwards it increases and then flat from 40 to 160. So you see that this is 24 is magnesium. So first peak is for helium, 2 helium 4, 4 beryllium 8, 6 carbon 12, 8 oxygen 16, then 10 neon 20, and 12 magnesium 24. So for all this there is a peak observed. So this is very interesting, why this peak is there, and what is the significance of this. So now you can look at some of the points, that is how you should write, describe average binding energy versus mass number curve. First you have to plot the graph of binding energy versus this, then you have to write like this: average binding energy versus a curve rises steeply at first for very small mass numbers, and then until it reaches 8.79 MeV at A is equal to 56, that is 2650 Fe 56, that is for iron. So maximum is for iron at mass number 56. Value is either 8.8 or 8.79 MeV. So first it increases slowly, then there is a peak, maximum is for iron, and then the curve drops to 7.6 MeV for higher mass numbers. The peaks are observed for 2 helium 4, beryllium 8, carbon 12, oxygen 16, neon 20, magnesium. And in intermediate mass is 40 to 160, where the peak is almost flat. Average binding energy is 8.8 MeV. So it is light nuclei fused to form fusion and heavy nuclei fission. So significance of these, that is 2 helium 4, 8, 12, 16, 20, 24. See, so the very interesting is occurrence of peaks at A is equal to, that is mass number 4, 8, 12, 16, 20. So if you check, say first example I will take, that is 2 helium 4. So 2 helium 4 follows A is equal to 4n. So that is n is equal to 1, first member. So 4 is equal to 1 is helium 4. Similarly, beryllium, n is equal to 2, it is 8, second member. So n is equal to 3, it is carbon. 4n is equal to 4 oxygen. 4n, n is equal to 5, it is 20 neon. 4n is equal to 5, 24. So this follows a very extraordinary stability of nucleus. These numbers are called magic numbers, which we will be studying in the shell model. And for these, so you can check 2 helium 4. So 2 protons, 2 neutrons. 4 beryllium 8, 4 protons and 4 neutrons. 6 protons, 6 neutrons. 8 protons, 8 neutrons. 10 protons, 10 neutrons. 12 protons, 12 neutrons. So these are the mass numbers, proton plus neutron. So for all these, helium 4, beryllium 8, carbon 12, oxygen 16, neon 20, magnesium 24, proton number and neutron number is same, which is symmetry. So it speaks about high stability of these nuclei. These nuclei are highly stable, and the symmetry is reflected in these peaks. Therefore, the binding energy curve is very, very important for our understanding of nuclear physics, and we can get lot of information just by plotting and understanding the binding energy, which is a curve of average binding energy, that is binding energy divided by mass number against the mass number of nucleons. So if you plot 0 to 250 mass number and 0, 2, 4, 6, 8, 10, this is the binding energy. So you know that slowly binding energy for light nuclei, it increases linearly, and there are peaks, and binding energy is maximum for iron Fe 56 mass number, it is about 8.8, and the curve is flat from 40 mass number to 160. So almost all mass number elements lying between 40 to 160 are stable, and the curve then drops to 7.6 at uranium, and the value of binding energy becomes 7.6. So this is what we have seen today. So we will stop here.